Thank you for joining us for this 30-minute webinar on dry powdered rheology for optimizing electrode manufacturing. Today's presenter is Behbood Abedi, a rheology application scientist at TA Instruments. Behbood specializes in rheology of time-dependent materials and their diverse applications, and has authored over 10 journal articles in the field. Without further ado, I'll turn it over to Behbood to start the webinar.
All right, thank you for your introduction. Hello, everyone. Let's just start it like this. I'm sure you guys know how lithium-ion batteries work. If I want to put it in the simplest way, is that we have cathode, positive electrode. We have anode, negative electrode. So anode normally made of graphite, cathode made of lithium-based compound. So then we're gonna need separator between these two because we don't want to direct short circuit between anode and cathode. But the separator should be kind of porous membrane that allows ions pass through. Then we fill between cathode and anode with electrolyte, which is a lithium salt, and we seal it. So we have a battery. So when you discharge the battery, you're using the battery, lithium ions go from anode to cathode, and we have electron flow from anode to cathode through the external circuit that power your device. Then inside the cathode, we have electrochemical reaction. These lithium ions and electrons combine and is stored in lithium compound. Now, when you want to charge your battery, you need external energy source to move these lithium ions back to anode. Also, the electron flows through the external circuit back to anode. And then in anode, you have the lithium ions and electrons combine and restore in anode. So now how we make these electrodes? So we're gonna need active material. Everything happens there. The release and the store of lithium ions happens there. The electrochemical reaction happens there. So we need active material. Then these active materials normally does not have sufficient electrical conductivity, so we're gonna need some conductive additive to boost their electrical conductivity. Then we're gonna need binder to hold this active material and conductive additive together. In a traditional way, then we need solvent to dissolve this binder, make a slurry, then you coat the slurry, then you dry it, then you calender it, and you have the electrode. But what is the issue with this process? Actually, there are some, but two major ones is that this is also very specific to cathode. The solvent it is used is really hazardous environment. It's an organic solvent, so you need to recycle that. That recycling is kind of a costly process. Also, this process of drying is time and energy intensive. So to enhance this process, they are thinking to remove the solvent and this drying process. So what happens is that, for example, for cathode that I mentioned, we're gonna have active material like NMC, conductive additive like carbon black, and binder like PVDF, and no solvent. So now we have dry powder cathode. And when we have dry powder cathode, so we're gonna have dry powder coating. And our major challenge here is that our knowledge, our science, our understanding of slurry is way more advanced than powder rheology and the understanding of how powder flows and the characterization of powders. So that's why exactly TA Instruments entered here and introduced this powder accessory to help to advance the powder rheology, our understanding of powder characterization. And the beauty of this accessories is that you have all together, you can do the flowability test, shear test, and compressibility test all together. It's really easy to change these geometries. It's really easy to load and trim the sample, and Trio software does all the analysis for you guys. So yeah, you don't need any other instrument using your HR rheometers. You can use this accessory. So previous week I was at SOR. I had great chats and talks with our colleagues in the community. What I learned was that powder rheology is really incognito in our community. So for the first part, I would try to show you guys more how this accessory looks like, what kind of tests we do, what analysis we do, what kind of results we would expect. And the second part, I would show you a case study on dry powder cathode, the NMC-based one that I did. And we go through it. So let's start with the powder compressibility. It's kind of straightforward. We have a cup. We have an upper geometry, which is a disc. So with rheometer, we can apply normal force. We know the gap. So as this pressure will compress the powder, we have changing gap. So we have normal force, we have gap measurements, we have the volume change, we can measure the compressibility. So your raw data will look like something like this. The green one is gap, the blue one is normal force. So you have the reference gap, for example, as 30 millimeters. So you put a normal force of 2 kilopascal. So you have a drop in gap, and then you would have a kind of steady state. The gap does not further reduce, so you cannot compress the powder more. So you increase the normal force a bit more 2 kilopascal. Again, you have a drop. The green one, you see it, the drop in the gap again until you reach the steady state. So you continue with this increment of 2 kilopascal normal forces and drop and the radius of gap and the radius of volume until at the max value of 20 kilopascal. You see here, you don't have further decrease in gap, so you reach the maximum compressibility of powder, and this way you measure the compressibility of your powder. And don't worry, these are raw data. You see here at the left top, the compressibility. You just one click, Trio does all the analysis for you guys. But I want to show you the raw data, what is happening in the background of those tests. And the through case study, we will see what kind of results Trios gives us. So yeah, the other test we can do is a shear cell test. Shear cell test is kind of well-known test. Is based on ASTM D7891, shear testing of powders. Maybe some of you guys have experience with Freeman rheology, powder rheometer. But as I mentioned, the beauty of this exercise is that you don't need other instruments. You can use your HR rheometers for that. So the first thing I want to mention that you can see in these figures too, for powder cell, your cup and upper disc is serrated. You have some veins on it because for consolidation you use the disc, but when you want to put shear, you want to grip on powder, you don't want to slip, so you have these veins on the geometry, which is different than the compressibility one. Also, how you do it, you start with the consolidation stress, that's a previous step. Then you have a pre-shear consolidation, and then you have shear at reducing normal stresses. So I will talk about it more in detail. So the first step you want to do is compress your powder. The consolidation is like an initial condition for that. So how you do it, you pour the powder inside the cup and your funnel, you put your desired consolidation stress, then easily you slide the funnel to the left and you have trimmed, your powder is ready to use. That easy. And after that, these are again raw data because I want to show you in more detail what's going on there. So you have in the left, you have some pre-shear analysis. So for this special test, for example, I have choose 0.015 megapascal as a consolidation stress. So actually, you guys that use rheometers have seen it. When you do a constant shear rate test, for example, for a thixotropic material, you have a kind of straight line with some slope, which is the elastic response. Then you have a viscoelastic response, which is kind of hump, that your yield point is there. Then you got a stress relaxation. Now for this test, if you want to repeat that yield point, it's very important that your initial condition is the same. We have the same thing here. You see here, these green ones are the normal stress, the blue ones are the measured shear stress. So for the reducing normal stress, before each step, we have the same consolidation stress because we want the same initial conditions. So we have the consolidation stress, then we reduce the normal stress to a value, and we put a very low shear, like 10 to minus 3 radian over second, and you raise the stress until we have the yield point. So you got the yield point. So at different, like here at 5 different normal stresses, you have 5 different yield points. So yield the stress point. So you have here 5 consolidation stress, which is the same value. You can get average of 5 shear stress values. So you would have 5 yield stress points at reducing normal stress, plus 1 average shear stress at consolidation stress. So 6.5 plus 1. And again, easily you see here, top left, you just can click on the shear and Trios does all the analysis for you guys. I will show you how this turned out. When we do the analysis, I just want to show you the raw data. So we're going to have 5 plus 1 point, but also this is the standard. There are more modifications we can do it. I will show you guys all of that. And then the flow cell test. We have a helical rotor. We fix the tip speed, and it goes all the way down inside the cup and then goes all the way up. So depending on the resistance of the powder, rheometer measures the torque and normal force it needs to go through the powder bed. So we can measure the total work or total energy that needs to go through the powder. This way, we measure the flow energy of that powder. But just one difference is here. This is a very important point I want to measure. In the shear cell, we had that shear, very low shear rate under consolidation stress. So we kind of analyze the flow of powder under relatively high stress. In this case, we don't have that high stress, so we are analyzing powder flowability under relatively medium to zero shear rates. And another important point is that when this rotor goes down, because the cup is closed, we have a confined flow, and when it goes up, we have unconfined flow. All right, so and also we have, these were accessories for room temperature. We have accessories at the, if you want to control the temperature, you use the concentric cylinder jacket. And you see here, you have the serrated one for the shear cell, the smooth one for the flow cell, and compressibility one. And if you want to use for temperature control, you see here at the right that this geometry with heat break. We use the heat break because we don't want that this upper part of the geometry contribute to the temperature measurements. And you see here these geometries have barcodes, so it's a smart swap. As you connect it to rheometer reads, trios reads these geometry, so pops up everything of powder and powder analysis, and you can do it easily. And anyway, if you have acquired this accessories recently, you want to do it, we have tech tips in our website that just shows you all the details how to set up these geometries, and it's really easy to use. All right, so let's now go through the case study that I did. As I mentioned, for dry powder cathode, normally the active material could be NMC, lithium, nickel, manganese, cobalt. So we need a conductive additive, which is carbon black, and we need a binder here, which is PVDF. So 96% of the powder will be fixed active material. So we want to observe that if we just change that 4%, different compositions of the conductive additive and binder, what happens? If that 4% can change anything in our powder characterization. So here we have sample 9631, which is 96 weight percent NMC, 3 weight percent carbon black, and 1 weight percent PVDF. So this sample has the highest amount of PVDF. And the 9613 is contrary, is 96 weight percent NMC, 1 weight percent carbon black, and 3 weight percent PVDF. So this sample has the highest content of binder, and the 9622 is the equal amount of binder and conductive additive. So let's just start with the, I just get more insight about these powders. This is the SEM image. These spheres are the NMC spheres, and you see here, this is the 9631, so the sample with the highest content of carbon black. You see here this network-like aggregation of carbon black between these NMC spheres, because carbon black is kind of fluffy and light, so 3% of carbon black is a significant volume. Yeah, this is how these powders look like under SEM. Just I want you to get more insight about it. So now let's start with the compressibility test. So this is what Trios gives you guys just with one click. And you see here the maximum of the normal stress of 20 kilopascal. That's very fascinating, these results, because you see here for 9631 with the highest carbon black content, the compressibility is almost 3 times of the sample with the lowest carbon black content and highest PVDF content. And the reason is that carbon black has the highest surface area to volume ratio, so they can fill the voids between those NMC spheres that I showed you, so they increase the compressibility. And compressibility is a very important element for powder coating. Shear test. This is what Trios gives you guys. You remember I mentioned 5 plus 1 points. We have the 5 shear yield stress points here from the reducing normal stress. So we fit a line to that. We call that yield locus line. The intercept of yield locus line with the y-axis is cohesion. Then we fit the first Morse circle to this yield locus line, which passes through the origin. Then at the intercept with the x-axis, we have the unconfined yield stress. The second Morse cycle is tangent to yield locus line and passes from that one point I mentioned. That is the consolidation stress and average of shear stress. So then here we have the major principal stress at the x-axis. So the flow function is the major principal stress over unconfined yield stress. And flow function is a very well established category just an index to categorize the flow of powders under relatively high stress. So you see here for the 9631, the flow function is around 5, is in the border of the cohesive flow and easy flowing, and for the 9613 is around 10 in the border of the easy flowing and free flowing. And the reason is that you see here the cohesion is higher for the 9631 is because of carbon black, because as I mentioned, it fills the voids there. Also, you see here, I did it in different temperatures, 37 degrees Celsius and 99 degrees Celsius, because I want to see how different geographical locations influence our data, like we do it in South Asia or Oregon, for example. So we can change the consolidation stresses. We can do the precision test to reduce that shear rate. It was 10 to minus 3 to 5 times 10 to minus 4. We can increase the number of points. You can do a lot of these things in the unlimited mode of Trios. That's very interesting. Although, see here, when we reduce the consolidation stress from 0.015 to 0.006 megapascal, your cohesion reduces, but so you got some voids between the particles that may induce inconsistent flow. So you reduce the consolidation stress, but your flow function does not raise, it lowers. So because you have some voids between those NMC spheres. So yeah, there are a lot of, depending on your process, there are a lot of uh, elements that you can change. And flowability tests, I really love these results because you do different tip speeds. Just imagine this tip speed, something analogous to shear rate. We talked about total flow energy of torque, so analogous to shear stress. So you see here, as we increase the tip speed, the flow energy reduces. So they are showing some properties similar to shear thinning. But the interesting thing is that for 9631, from the lowest tip speed to the highest tip speed, you have 46% decrease in total flow energy. But when 9613 that has more binder, it kind of holds the structure together. So at low tip speeds, you kind of have plateau. And then above 40 millimeters per second, you start to have decrease in the total flow energy, but it's like 20%, half of what happens for 9631. So it kind of holds the structure together, does not let that the structure just be destructed totally. But also, so there's one thing you would think of it. What happens to your conductive network if your flow energy reduces 46%? So yeah, you see here also for the other compositions, same thing. You see shear thinning behavior here, but depending on the binder content and the carbon black content, you have different degrees of shear thinning. So there's a fine line. You tune your powder that kind of sometimes shear thinning is desirable. You want it because of better coating, but you don't want your conductive network disappears. And so I'm going to wrap it up here. Just the final remarks. This most important thing is that many people just focus on binder, but the carbon black role is as important as binder. You see all powders show some shear thinning, but for the powder with the highest content of carbon black, we saw like a huge reduce in total flow energy. So as a rheologist, I would suggest you guys go check your conductive network. And yeah, we can measure the flow function under highest stress, medium stress to lowest stress, depend on your process or coating. Sometimes maybe it's desirable, sometimes it yields to your overspray. We can regulate those things. And yeah, thank you all. And if there's anything we can discuss, any questions, I will be happy to answer that.
Thank you, Behbood, for that great presentation. We will now take a look at questions. Please remember to continue to submit your questions through the question box. Our first question is, are there inline rheological measurement techniques for powdered rheology?
Sorry, would you inline?
Correct. So the question again is, are there inline rheological measurement techniques for powdered rheology?
I don't know what they mean with inline rheological measurement techniques for powder rheology, but what we offer is these tests that I showed you. And yeah, these are what we can do now, what accessories we have. And yeah, this is all we do now. Well, we'd be happy if they can explain what they really want to know.
Fantastic. Our next question is, what's the minimum amount of powder I need for the test?
Oh, that's an interesting question. Depends kind of on the geometry. For shear cell, above 15 cc, for flow cell above 20 cc. Especially, but if you want to do that under the temperature controlled environment, I would say more than 20 cc.
Thank you. The next question is, can you explain more about the relationship between the conductive network and decrease in energy, flow of energy?
Oh, yeah. You know, because I showed you the carbon black raises the cohesion of our powder. So cohesion also kind of increase the flow energy you need for the powder to flow. So when you see this huge drop in the flow energy, so it means that that network-like agglomeration of carbon black is destructed, because if it was still in place, so you would have higher flow energy. So when you see that abrupt decrease in your flow energy, it's very important that you have in mind that your conductive network, that network-like aggregation of carbon black, is not like when it was at rest. So it's very important that you check now your conductive network, because you see it in rheology that that cohesion, that aggregation network-like is not in place anymore.
Fantastic. Our next question is, what is the recommended temperature soak time for powders?
Oh, yeah. You know, when you do in rheology, you do the test between very small gaps. So the volumes are lower and the liquids are better conductive for temperature. In powder rheology, you do like 20 cc of powder. So you need higher temperature soak to reach the steady state. We normally would recommend half an hour for that.
Great. The next question is, do we observe behavior similar to shear thinning only in confined flow energy?
Oh, yeah, yeah. You know, let me go back to this thing. For confined flow energy, values are higher because you are going through the cup, which is bottom is closed. Unconfined flow energies, you have lower values, so the differences are smaller. But if you look at these results, these square ones with our unconfined flow energy, you see here for 9631, it starts above 9613, but over time it goes below it. For 9613, you kind of have a constant values, but for 9631, starts from higher, then goes to lower. So yeah, we have shear thinning for unconfined flow energies too, but it's kind of less tangible. Yeah, but yeah, we have it, especially when the powder is cohesive.
Great questions and great answers. Our final question is, once I conducted a shear cell test, but the analysis did not show the first Mohr circle, what could be the reason for this?
Yeah. You know, when your powder is not cohesive, so sometimes your cohesion value is very low. So in this intercept at y-axis, it may go even negative. So you cannot have your first Mohr circle. So what would we suggest is that use more points here. If that 5 points I mentioned, you can raise the number of those points, have more data points. Or when you do this and always get the negative cohesion because your material is not cohesive at all, so you are at the free flowing region, the flow function over 10. Yeah, just can say that you're at free flowing region.
Thank you for that answer. We do have a bonus question. How will the mixing history influence the measurement?
But that's a very great question too. So powders are really heterogeneous. Uh, what we really recommend is that because we want to delete that history, is that especially for compressibilities and flow tests, we normally do a one pre-flow conditioning, just at the average taper speed, just go all the way down and all the way up to homogenize the powder and just delete the shear history, the mixing history, because as I mentioned, we want an initial condition for all our tests. So that's what we suggest to do, that the preconditioning flow just up and down, like at 60 millimeter over second speed, just to homogenize your powders.
Well, thank you again, Behbood. And thank you again for joining us. Don't miss out on our next webinar, Optimize Electrode Slurries via Flow and Structure Analysis using Rheo impedance spectroscopy next week on October 30th. Registration is via the link in the resource box, and please contact TA Instruments with any additional questions.
Thank you all also.